Hi everyone, my name is Trapp and I'm a graduate student working with Dr. Dushan Quresh at the University of California, San Diego. In this video I'm going to give a quick overview of a paper that we'll be submitting soon on the accretion and radial transport of gas in the fire simulations. The core problem we're addressing is the fact that in order to maintain observed star formation rates, galaxies need a supply of gas to central star forming regions. To address this, we analyzed 4 Milky Way-mass galaxies at late times in the recent Fire 2 cosmological zoom-in runs that incorporate magnetohydrodynamics and cosmic rays. As Dr. Kresh mentioned in his talk, these cosmic rays provide a non-thermal pressure source in the halo, which limits inflows and lowers the star formation rates in these disks, bringing them closer to observed values. We characterize the radial and vertical velocities within these galaxies, as well as how and where the gas joins the disk. We additionally look at how gas within the disk is able to move inward and fuel star formation at small radii. While I won't discuss it here, the paper also makes comparisons to other Fire 2 simulation suites without cosmic rays, as well as making quantitative comparisons with existing observations. So these are our 4 simulated galaxies we'll be focusing on. They all have similar halo masses but different disk sizes. One of the first things you'll note is that they all have very pronounced edges. The H1 and molecular column densities drop off very sharply at the disk edge. Please note that M12F underwent a recent merger event with an LMC-like object, making some of its characteristics a bit different from the other galaxies. It's also important to note that we define the disk edge as the radius where the total hydrogen column density drops below 10 to the 20.3, which we show with the white circle. This radius will be referenced as RDLA in upcoming figures. So what does the radial velocity of this gas look like? Here up top we just have a face-on view of these galaxies. The red or positive values show outflows, while the blue or negative values show inflows. Note that these instantaneous values are relatively high, about 40 kilometers per second inside the disk and higher outside. When we average these values around the disk and over time, we get a more gradual net inflow. On this top row of plots, we show the radial velocity curves averaged over time. Note that the x-axis is the cylindrical radius normalized to the size of the disk. Outside the disk, we see inflowing radial velocities on the order of 20 kilometers per second. At the disk edge, however, there's a transition and things begin to slow down to 1 to 5 kilometers per second on average. The bottom row shows the corresponding radial mass flux. So what does this look like in angular momentum? This top row shows the average specific angular momentum of the gas. The red dashed line shows the rotation curve calculated from the enclosed mass. So interior to the disk edge, the gas is fully rotationally supported. Outside of the disk, the specific angular momentum still increases with increasing radius, but it's much flatter. So it's not fully rotationally supported. This bottom graph shows the relative orientation of the gas's angular momentum vector with that of the disk. Obviously the gas within the disk is aligned very well with itself, but even going out to large radii, the gas remains roughly aligned, down to around 80% so at twice the disk radius. So now we want to ask at what radius is the gas actually joining the disk. To do this, we did particle tracking on the accreting gas mass elements in our simulations and quantified when and where they become part of the disk in 2 ways. The first is geometrically, so when a gas mass element passes below 1 or 2 scale heights of the gas disk and remains there for at least 1 orbital period. That's shown in the black and blue histograms. The second is the radius at which the gas becomes fully rotationally supported and remains so for at least 1 orbital period, shown in the green. In both cases, we find that the gas generally joins the disk slightly interior to the disk edge. We want to note that when we normalize these plots by surface area, the distributions are relatively flat. So the gas tends to join near the edge of the disk, but what do the trajectories look like? In general, we find that the gas is coming in at small, non-zero angles above the disk plane. The gas that joins the disk closer to the center is doing so more vertically, as can be seen by the redder lines in the plot. We also want to note that these trajectories tend to be coming along parallel to the disk at larger radii before falling in when they join. This results in the angle slightly increasing as they accrete. So to quickly summarize our key findings, our galaxies show a sharp cutoff in gas density at the disk edge. This transition in gas density also corresponds to a transition in average radial velocities, with gas outside the disk coming in at high radial velocities before piling up and slowing down within the disk. This also corresponds to the transition between gas being fully rotationally supported within the disk and lacking rotational support outside of the disk. As gas accretes, it tends to join the disk just interior to this edge at small but non-zero angles above the disk plane. Thank you for watching.